Okay, welcome back. This is the last video of the year, last teaching new topic video of the year. Pushdown automata. What are pushdown automata? As I mentioned in the previous video, they are an extension of the concept of finite state machines to deal with more complicated languages. So just like a finite state machine was a theoretical model of computation and it had certain powers, pushdown automata have more powers, and they can be used to recognize context-free languages. Alright, so I'm not going to dwell on the theory too much. I'm going to jump right into an example, and we'll sort of just talk out this example, and that will be it. Just kind of one example. Okay, so let's take this language, this same language which we keep sort of trotting out as the simplest language, which is not regular, and we saw in the previous video that this language is in fact context-free because we generated it with a context-free grammar. Well, we can also come up with a pushdown automaton which recognizes it. Alright, so how does this pushdown automaton work? Well, I'm going to draw it now. What you have are, once again, a set of states, and some of those states are accept states. Here I'm going to present a machine with 4 states. And here they are. And okay, I'm gonna, well, okay, I'm gonna just do this kind of casually. So here's Q4, okay. And so far, this seems not unlike a finite state machine. We have a certain number of states. We have certain transitions which take us from state to state. We are, once again, processing a string, one character at a time. And based on what that particular character that the sort of cursor is on is, we transition from one state to another. Okay, but now we have something extra. We have a stack. And okay, fortunately everyone watching this video already knows what a stack is, so I don't have to explain. But it is yet another sort of theoretical device, which it's kind of a list or something like that. And the stack is empty at the beginning, and you push something onto a stack, and then you push new things onto the top. And then when the phrases are push and pop, you push a character onto a stack, and then when you pop something off the stack, it's the thing that comes off is always the last thing that you pushed in. And then okay, so So if we want to go into sort of a little bit of theory, what is one of these pushdown automata? Well, it's now like a 6-tuple or something like that, right? Because there is now, I'm just winging this, there is an alphabet, sigma, but there is also a set of states. That's not S. No, that's I. Oh man. There we go. There's a set of states S, and there, which in this case is just Q1, Q2, Q3, Q4, obviously. Then there is, what else is there? Normally there would have been a start state, a transition function, and a set of accept states. Okay, so now we add one more thing, which is an alphabet of characters which can be pushed onto the stack. So I think it's helpful to avoid confusion to use, you're using the stack to kind of keep track of what's going on. So at least in my examples I'm going to use, I'm always going to use different characters. So let gamma be some possibly totally different alphabet of characters which can be pushed or popped on and off of the stack. Okay, and then we have the transition function, the start state, and the set of accept states. Okay, so alright, this is the start state, same notation. We indicate the set of accept states is of course going to be a subset of the total set of states, and we again indicate those with the double concentric circles. Okay, but now this is where it gets kind of exciting, because now, and okay, maybe this is not so hard. We are going to, when it comes to our transition function, we are going to now have more power, because our transition function is not just going to tell us from a particular state, reading a particular character, what new state to go to, but what state we go to upon reading a particular character from a particular state can also depend on the character which is on top of the stack. And so you may sort of look at the stack, so to speak, and see what character is on that stack, which is to say you pop it. The only way to look at it is to pop it off. And while, so that's the thing. And then additionally, in each transition, based on what's on the stack, based on what state you're in, and based on what character you read, you transition to another state, and you perhaps push something new onto the stack. And so, for those of you who want this to be expressed more formally, t, the transition function now, takes sort of three inputs. So it's going to be a function from the set of states and the alphabet and the set of characters from your stack alphabet to ja, ja, ba, and cha, cha, cha. Okay, and so I'll just say really quick, what does this mean? It just means that this function really sends an ordered triple to an ordered pair. The ordered triple is what state you're in, what character you just read from the input string, what character is on the top of the stack, and the output of the transition function is what to pop onto the stack and what state to go to. And you can also feel free to not push anything onto the stack or not to pop anything, and for that we use the null string. So we think of ourselves as always pushing something onto the stack and popping something off, even if that thing is in fact the empty string. And if you actually just want to leave something on the stack, but you want to look at it or something like that, then you just sort of you pop it off and you push it back on. Alright, so how does this work? Well, we still have the ability to sort of clearly label what's going on, because we can still sort of capture what state we're in and what state we should go to next. But now I need to sort of build in to my labels here sort of three additional things. Whereas before we would just label the arrows with, hey, what input character did you just read to follow that transition arrow? Now we need to label the transitions with basically with the red. I guess it is good that I sort of wrote this. Because so sort of what state we're going to, from what state we're in and what state we're going to is captured by the visual diagram, but it's sort of this feature which is going to need to be on the label of the arrows taking us from state to state in the diagram. Okay, so let me explain. Alright, and I think this is pretty standard for everyone to do this, but if not, I want to make a standard for this class. It's really good to not assume that your stack is in any particular state when you find it. I think we can just assume that the stack is empty, but we also have no particular way to know if the stack is empty. And maybe if you try to pop something off of a stack that's empty, maybe something sort of bad happens. So it is a good habit, and it certainly helps clarity, if we create a special character, and I'm just getting this from this book, this author uses the pound symbol. So the hashtag or whatever. So the pound symbol, let's use it as a special character in our stack alphabet to indicate that we're on the bottom of our stack. Alright, so the very first thing I'm going to do is kind of a weird thing to do, and it's something that we're just going to do basically every single time. For every one of these pushdown automata, we're going to do this, which is we're going to create this transition that says lambda lambda goes to pound. And the way to interpret this is read nothing from your input string So that's the idea of the lambda. This lambda is acting just like the old lambda in our non-deterministic finite automata, which is to say, do this without reading any characters from the input string. The second lambda says, don't pop anything from the stack, or you could think of it as popping the null string from the stack, which is to say, don't pop anything, but push a pound sign. So the very first thing we're going to do is we're going to throw a pound sign onto that stack. And if we should ever encounter a pound sign again, then that's equivalent to saying that our stack was empty at that point. So it's a way of detecting later that our stack is empty. Okay, let's now do some real things. Okay, well maybe we should have just talked about the sort of the big picture of this. Why does a stack intuitively suddenly make it possible for me to recognize this language? Well, the whole reason why we said that a finite automaton couldn't recognize this language is because there was no way of keeping track of how many A's we had read so far. If you read 350 A's, then I need there to be 350 B's precisely, which follow after that, and I would have to sort of remember that somehow, and there was no mechanism within the finite state machine system to do that. But now we have the mechanism. The mechanism is the stack. And so, loosely speaking, what are we going to do to recognize this language? Well, it's quite easy, I think, right? Every time you read an A, you pop a character onto the stack, and you just keep reading A's, and every time you read an A, you push a character onto the stack, and every time you read another A from the input string, you just push another character onto the stack. And by the time you're all done reading all the A's, you now have a huge stack full of some marker which has told you how many A's there were, and now you just can start reading the B's, and you pop, as you read each B, you pop something off you pop one of those characters off the stack, and if the string is to be accepted, then you should end with yourself popping off exactly the same number of characters as you pushed on. That's a way of figuring out that they're the same number of B's as A's. Okay, so that's like the big picture. Okay, so the first thing we're going to do, so what is state Q1? State Q1 is the state of, dude, this machine just started. And note that I've made it an accept state because the null string is a string of this language. But then, basically the very first thing we do is we push onto the stack a pound sign. Okay, and now we do exactly what I said we were going to do. We read A's from our input string, and for each A, we push a character onto the stack. For clarity, I think we should push a different character. So I can squeeze this in here. So I invented alpha. So let alpha, yeah, that looks fine. Let alpha be a character associated with A. Let it just be a new symbol, a symbol of my stack alphabet, which is associated with A. And so I'm doing now exactly what I said I was going to do. I'm reading A's from the input string. I am popping nothing, hope I said that right. I'm popping nothing in the previous problem. I'm popping nothing from my stack, and I am pushing onto the stack this alpha. Okay. Well, good. And you just keep doing that until you've read all the A's. And when you've read all the A's, now it's time to start reading the B's. And so this transition is going to tell you what to do when you hit a B finally. And the answer is, I guess I'll do it over here. So B, alpha, arrow, lambda. So now it's just the reverse. Now for each input character B from my input string, I should pop off of the stack alpha and push the null string, which is to say push nothing. So more casually, I am just pushing an alpha for every A that I read, then I pop an alpha for every B that I read. And then, sorry, that was a little bit confusing. That's all true what I said, but in fact we only do this rule once. I sort of misspoke a little bit. Q2 is that we should describe what these states are in words. Q1 is the state of I've done nothing yet. Q2 is the state of I'm reading my A's now. Either I'm about to read my first A or I've been reading A's for a while. State Q3 is the state of I'm reading my B's now. And so Q3 is the state that I stay in for a long time, over and over again, reading a B and popping an alpha, pushing nothing. And this transition from Q2 to Q3 that I was describing only gets executed sort of once per string. And so it's the sort of the rule you follow to get from the state of I was reading A's to I'm reading B's now. And I guess the empty string is accepted by the machine by sort of doing nothing, but every other string will have at least one B in it. And so you have to at least follow this rule to get from Q2 to Q3. And then you may follow subsequent rules staying in Q3 if there are more B's. Alright, now, well, what's supposed to happen? What's supposed to happen, ideally, if the string is to be accepted, is that we finish by just barely popping off the final alpha as I read the final B character. And so if this is my accept state, it takes a very particular set of circumstances for me to successfully get to this accept state. I need to be at a point where I have completely finished my input, processing my input string, and I've popped every alpha off the stack. And so here's our rule for that. It's lambda pound to lambda, which is to say, go to this accept state if you read nothing from the input string. You happen to be at the bottom of the stack, so we've re-encountered the pound character that we pushed onto the stack at the very beginning. Pop that off and push nothing onto the stack because whatever, we're done. And if so, just go to the end. Okay, this is the right answer, and we have in some ways kind of put on blinders. This is how I think about it. The task of writing one of these, you sort of just kind of go tunnel vision straight ahead towards the successful goal that you want. And by that I mean, I just sort of wrote the path through the machine that I would like, that I sort of anticipate being accepted. In fact, what I have done is I haven't thought too much about strings that this machine shouldn't accept. And now I think there's quite a bit of sort of understanding that's still left to do here. Let's check the time. Because it's not clear what's going to... I think it's relatively clear that this machine is going to accept all the strings that it's supposed to accept. But it's way less clear to me that this machine will not also accidentally accept a lot of strings that it isn't supposed to. And what's the sort of deep thing that you have to appreciate is that this pushdown automaton is like fundamentally non-deterministic. So, and I don't really know what that means, so maybe I should step back from that. But sort of non-determinism is kind of built directly into the definition of a pushdown automaton. And so, if really the set of transition rules if really the transition function is an ordered triple from every state and every input character and every character from my stack alphabet to every state and every character of the stack alphabet, then really there are quite a lot of transition rules out there. And you know, here only 1, 2, 3, 4, 5 of them are being depicted, which is to say, any one which is not depicted, then the machine's just going to die. So just like with finite automata, or just like with non-deterministic finite automata, we sort of freed ourselves from the psychological burden of listing out what to do with every input character in every state. And if the string is just not meant to survive a certain input character from a certain state, we simply neglect to mention that transition at all, and it's just assumed by default to die. here, that same thing is going on, but now it's even more extreme because now, for every combination of input character and sort of what's on the top of the stack, we could potentially have a rule. And so whenever that rule doesn't exist, the string dies. So there's a lot of dying going on. And I think what we should now do is we should just talk out some strings. Okay, so let's go. I find this to be really hard. I figured this out sort of with my students. So what we're now going to do is we're going to trace through some strings. Okay, well the empty string, we kind of just talked about that already, right? The empty string is going to be accepted in state Q1 immediately, and that's it. Okay, let's take a simple string which should be a string of this language, like A, B, B, B. Okay, let's go through, to make sure we understand the machine, let's go through and trace this string. And okay, I think this part is maybe not so hard. What do? We start at the beginning. We push we read no input characters, we pop nothing off the stack, but we push a pound sign. Okay, so now the stack has a pound sign on it. Now we're in state Q2. What do? We read an A, pop nothing, push an alpha, and we go back to Q2. Now we've read one A. And we just do that 2 more times. So I do jump, and now I'm in state Q2, and I've processed A, and A, and my stack looks like, on the bottom there's a pound sign, and then there's 3 alphas on top of that. Okay, and then we go to, then we're about to read a B. And so we follow this rule. This rule says, hey, if you have a B next, and there's an alpha on the top of your stack, then push that alpha, and, pop that alpha, and push nothing. Okay, so now we do exactly what we intended to do, is we read a B, and we pop 1 alpha off the stack. Now we go to state Q3, and we're in the state Q3 with now the stack looking like pound sign on the bottom, then 2 alphas, and there are 2 B's left to read, and we stay in state Q3 2 times, reading those B's, popping alphas, and pushing nothing. And so exactly what happens is what's supposed to happen is we're in state Q3 with no input characters left to read, and nothing left on the stack except the pound sign, and that's exactly what this rule tells me to do. That if read no input characters, just pop that pound sign, push nothing, go to state Q4. And crucially, in state Q4, there are no characters left in the alphabet to read. And when there are no characters left in the alphabet to read, the string just stops processing. And if you find yourself in an accept state, I think it's irrelevant what is on the stack. God, I hope that's true. I think that's true. When the string is done processing, then you are in a certain state. And if that state is one of your accept states, then you just accept. So we do accept the string because the string sort of ends, so to speak, or it finishes processing in state Q4. Okay, good. So I think that's pretty clear. Okay, let's do one that doesn't work now. And there are sort of 3 ways that it cannot work. There's this A, B way. So let's do that first. So this is the situation in which it is true that the string has all the A's followed by all the B's, but it has too many A's and not enough B's. Okay, well, going a little faster now because I think we get it. We start at the beginning, we push that pound sign, we go to state Q2, we follow this rule 3 times, pushing onto the stack alphas for each of the 3 A's. And then we exit state Q2, following this rule, and what does this rule do? It reads a B, and it pops 1 of the alphas off the stack. So now we are in state Q3, and if you're following everything that just happened, I think you should. We're in state Q3 right now. We have finished processing all of our input string. And what's left on the stack is 2 alphas. because we pushed 3 alphas onto the stack, but we only pushed we pushed 3 alphas onto the stack, but we only popped 1 of those alphas off. So now there are 2 alphas left on the stack. And now we're in state Q3. So the string has finished processing. And since the string has finished processing and Q3 is not one of the accept states, I have previously said that the string should just die. And I guess by die I mean, you know, the string is done. The string is finished processing, and so we end in state Q3. Q3 is not one of the accept states, so this machine rejects that string. But you might wonder, hey, what about this lambda transition? Don't I get to do lambda transitions for free? Ah, yes. You can transition for free from state Q3 to state Q4 without reading any input characters, which is to say that even when the string finishes processing in state Q3, you're allowed to, like, you know, just before dying or something, follow lambda transitions to other states. But only if you're at the bottom of only if you can pop off the stack a pound sign. And we can't pop a pound sign off the stack, because pound is not on the stack. There are 2 more alphas on the stack. Or really, the best way of putting it is the top character on the stack is an alpha. Okay, good. So this string fails, and as it should fail, it fails by making it all the way to Q3, and in Q3 there are still alphas left on the stack, and so when the string finishes processing, we just never get to apply this rule to get to Q4 because we haven't re-encountered the pound sign. Okay, now there is another way that this could go, which is A, B, B, B. What now? Well, this, of course, string should also not be a string of my language, or just isn't a string of my language, so this machine should not recognize it. Okay, what happens? We start. We push the pound sign. We go to state Q2. We read an A, and we push onto the stack 1 alpha. Okay, and that's it. Then we follow this rule, which tells us to read a B, to pop that alpha off the stack and to push nothing. So now we're in state Q3, and if you're following this, we're in state Q3 with 2 B's left to read. So we're not done processing the string yet, but in fact we have popped all the alphas off the stack, and so the only character on the stack is the pound sign. And we're in state Q3, but note that in state Q3 I have a rule for what to do when reading a B character, and that there's an alpha on the stack. Sorry, what happened? Oh yeah, I have a rule for what to do when reading a B character, and there's an alpha on the stack. But what is actually on the stack right now is just the pound sign, because I pushed 1 alpha, but then I popped it off again. So I'm sitting here with 2 B's left to process, but the character on the top of the stack is pound. And so if the character on top of the stack is pound, note that from state Q3 there's simply no rule for what to do when we are reading a B and the top character on my stack is a pound sign. And we are to interpret there being no rule as being the rule is like we die. So you can create some sort of black hole state if you would like to capture the fact that whenever the rule is missing, the actual rule is to say to go to the black hole state and die. But okay, that's sort of confusing or distracting or something like that, so no one does that. So what happens to this string? This string dies in state Q3. It dies in state Q3 with 2 B's left to process because there's simply no rule for how to process those 2 B's. The only rule for processing a B is when there's an alpha on the stack, but alpha is not on the stack. Pound is on the stack. Now, it's a little bit more subtle than that, because we have this nondeterminism rule, which says at any time you can pass into, like, Nirvana, Shangri-La, whatever, heaven over here, the state Q4, this accept state. You can pass on to there by reading no characters if there's a pound sign on the stack. And there is a pound sign at the top of our stack. That is the character that we're reading right now, because like I said, we pushed only one A and we popped it again. So now we do actually, one sort of path in the non-deterministic tree of this machine dies in state Q3 with no rule as to what to do when we read a B. But another path through the machine does in fact make it all the way to Q4 by following this rule, which says read no characters, and pop that pound sign, push nothing. But now we're in Q4 and there's still 2 B's left to read. And so though I make it to state Q4, I die in Q4 because there are no rules for leaving Q4, and I don't get to enjoy the status of Q4 as an accept state unless I get to Q4 with no characters left on my string. That's only then do I look at the list of accept states and see if this is one of them. But here, in fact, I'm not done processing my string. I have 2 B's left, and so those 2 B's mean that I have to follow some rule to process them, and there are no rules for what to do when you're in state Q4 reading a B, and so we go to the black hole state and we just die. Okay, so we sort of die in Q3 and Q4 simultaneously. Every path of that machine dies, so we die. Oh my god, last one! So okay, so I'm gonna go really fast now because I want this to be like 1 minute. Take 1 minute. What if the string is in fact like even worse? What if it's just like not even in the form a bunch of A's followed by a bunch of B's? Well then, let's see, we go here. We go here. We have pushed that pound sign. We're in state Q2. We read an A and we push an alpha. So now we're in state Q3. There's an alpha on the stack. Now I follow this transition from Q2 to Q3 by reading that B character, that second character of the string, and popping that alpha off. But now I'm in Q3 and I'm reading an A. And there's just no rule for what to do in state Q3 when you're reading an A. Because you're just not supposed to be in Q3 if you have A's left to read. And so the lack of, just like the previous example, the lack of any direction as to what to do in state Q3 when reading an A means that we die in Q3. But we also non-deterministically go to state Q4, which we're allowed to do because the stack is empty, or has a pound on it. But then we also die in Q4 because there was still an A, B left on my string. Okay, that's it. Goodbye!